FunctionGemma. We are talking about 270 million parameter language model, and we are going to teach it to make structured decision for any use cases. Google has released something really phenomenal. A model whose output is an executable function which can be called by conditions on any conversational prompt. This is the modern AI stack in action. And we are talking about the same Gemma 3 270M model that got released 2 months back. It was a language model which is further being fine-tuned by Google to make it precisely work for frameworks, insights. Google really wants to make something that is truly actionable. In this video we are going to see a lot of things. We are going to see a Gemma 270 base million parameter model working on without fine-tuning, how it is performing, and after fine-tuning you will see there is a significant improvement in the accuracy of any action task that we are trying to perform. This model is on the base itself is very much capable, but we are going to explore it. How can we fine-tune it on our dataset, in fact on any dataset. So what traditional language model works like, it takes an input, generates an text, and then it's up to the human interpretation. They takes the action. This is something slightly different in FunctionGemma. Takes an input, makes a function call, and it generates a system action. So to make you understand what is system action, look at the screen, a demo from Google itself, how a conversation is creating Google Meeting apps, meetings, and how it is opening Google Maps. The voice are getting translated, those translation are getting converted into action, which is executing a piece of software in API calls, and it is resulting in a meaningful action that is visible from and by the way, this is running completely local on device, on a Pixel phone, and this is something really incredible. And then after I tested this really cool playground from Google itself, where they have created essentially a game where you can add a prompt, and it just create a game artifact on the fly. So let me type a wide line at bottom so that this ball get bounce, and it just created an artifact. It's slightly offset. Let me center it. Let me modify a prompt a little bit. Add a wired line at bottom's center. This should work. So on the fly it just created a game artifact. So how cool is that? Like, we are talking up, and this is by the way happening in my browser itself, completely local. So what we are going to do, we are definitely have understood the capability of Gemma, and Google has also provided an example how you can fine tune. You can probably follow that, but that something is it's good to learn, but when you're engineering something you don't have that flexibility of I would say a toy dataset. So we are going to go completely wild, and we are going to collect data from an open source contributor company, OpenFoodFacts, one of the best highly contributed project that I have seen. This project is all about foods and product. They also have a sub brand for cosmetics and all, but we are going to focus on the food one. They essentially have collections of all of the food packaged product where people make contributions, and they are actually adding all of the ingredients of any product. Like they capture the picture, the barcode, all of the essential informations like their ingredient tag, and then based on that, in Europe you'll see there is a Nutri-Score idea around where A is better quality and E is lower nutrition quality and all. There's also a Nova rating and all. So if you see, there's a lot of valuable data that we can collect and make an LLM work on that and make decision on behalf of ourselves. So here's the plan. Like what we are going to build, it's a food compliance decision agent, which is going to take this raw data and it is going to take a decision on our behalf, like whether this food product should be approved, and flag it for a manual review. That's pretty common. Request for more information, reject if it's not a very high nutritional food. So it's very interesting project, and we are going to actually, so if you coming from an AI background, you pretty much know an L agent in language model can also do that, but making a functional call to specifically for these things can make a big difference. Like when you do an approved product, where you can further take this beyond, like you can add this to a cart, make an system where this agent is the first layer, and you care about your customer. You don't want any food product to be onboarded onto your system where the nutritional score is bad, so you put that layer of agent in front of it, and if it approves the product, then you invoke an API which is going to insert that product into your database. So something like this is possible, and this is what we are essentially going to do. We are going to collect the raw data, and we are going to prepare our dataset for this specific task by ourselves. So no, in production setting this is usually done by human, but we don't have that liberty. So we are going to learn how we can create a synthetic data, and then we can use it to do a supervised fine tuning using transformer reinforcement learning module. So I am going to link this Google Colab in the video, and I'll make sure that this happens as soon as this video is uploaded. So what we are going to do is you have to just make sure you have to go click on these runtime, manage session. There is no active session running. Change runtime type and make sure that it is T4, and then you can connect your runtime. So we do need GPU for this fine tuning. Once this is connected, you'll see green tick. You need to install transformer, dataset, TRL, and accelerator centerpiece, and protobuf, since the sentence pins handles subword tokenization, and protobuf serialize the vocabulary. So we need that. And once they are installed, let's import these dependencies. And so we have actually, what I tried to load whole data set, but it become a very long session, so I'm going to just pull few samples. You don't have to mention any limits if you want to do complete fine tuning on a whole data set. You can do that as well, but I'm going to limit to 10,000 record. So what is actually happening here is, from OpenFoodFact, we are pulling all of the data set. We actually wanted to pull all of the data set, but actually we are just streaming the only few portion of the data set, which is 20,000 sample size, and from that list we are going to do sampling of 10,000 example using .take, and it convert it to in a in-memory database, because we are going to map over this multiple time during pre-processing, and we don't want to rescan each item again and again. So let's run it. It's going to download the dataset, and this dataset, each product, we are particularly interested in the product name and ingredient text, the completeness, how completed the information is, and nutritional score, and there is also a flag which they do pre-processing, and they tell us like whether this is completed or not. This is going to be very helpful. And then we are going to make a functions which our LLM is going to execute. Right now they are not doing anything because this is not the point. We want to make our LLM to select an appropriate function. To do that, you need to write a good doc string. you need to provide a description and the arg, and you need to define the those argument. And this is really very important because in you'll see we have imported get JSON schema. Let me show you from transformer utils, and this is something that bridges the difference between Python function and a structured format that models need to learn. So once this is done, we will actually are going to use convert them as a tools, and then we are going to pass this into a chat template. So it's pulling the data. It should not take more than 5 minutes, I guess. And once this is done, I'll explain you what more things that is required to be done. So let's wait for it to happen. You can see we have got the 10,000 samples, and this is the default keys, and all of there's a lot of information that is coming, and you can probably use them, but as I told you, we are going to use few of them. So let's do the invocation. Okay, there is one error. Let's fix it. I believe, yes, is not defined. So there was just a missing input, so we fixed that. Now this is where it gets interesting, because get JSON schema uses Python type hint and docstring to generate OpenAI compatible function schema. So under the hood, it's doing an introspection. What is the type of function description, parameter it requires. These whole things are getting formatted as JSON. So this JSON schema is what is going to inject into the model context. The model learn to generate output that conform to the structure, and it's essentially constrained generation, but though learned behavior rather than forced decoding. So this is important. So now we'll need to understand what the decision logic synthetic label generation. So this is our labeling function. In the production setting, you would use human annotation or log decision from production system, but for demonstration and honestly for a lot of business logic, that's already codified. Deterministic rule works perfectly. The hierarchy, the data completeness check, what we are doing is, if the data completeness check is less than 60% or critical fields are missing, then we request for more information from the user itself. So it's going to be routed to the different tool call, so which is going to be this request more information. And this is going to be the quality gate, where the nutrition grade is less than E, then this is going to be flagged for human review. And there is an approved product, which meaning that it meets the quality standard. So this is something which is going to, and you can make your own business logic as well. So now let's define the system prompt for the model. Gemma 270M. You are a food compliance AI. You must choose exactly one action using the functional calling. This is going to be the system prompt, and see how the decision is built. First, we are calling our decide action. It gets the decision, and then this is the user context: product name, ingredient, product completeness, nutrition grade, and this is what we are preparing here. So this is something the output of the model should look like. So this is what we are preparing ourselves. We are putting a system prompt, the user context, and the decision which tool to use. Since we have codified, so we will get the correct tool name and the argument that needs to be passed, and the whole tool list. So this complete, This is our JSON object when it goes here, so this is going to be present over here. So now we just have to call our dataset to map this build conversation, and we need to remove the original columns, and let's do that. It's going to prepare the data. I have clicked over it and it's just mapping this conversation here. There was an error. I have annotated the fix. So actually we have to JSONify the argument, then it fixed the problem. Now let's look at one of the thing. It's like name of the tool, type function. So perfect, this is what we want. So now we need to log in to our HuggingFace, and you'll need to request and paste your token like this. I'm going to revoke this obviously, otherwise you won't be able to access the model. You need to have the login, and it's loading the model. Safe tensor is about 536 MB. Perfect, it's done. And let's run our evaluation function. This is our inference pipeline. It is just doing the tokenization of chat template that we have prepared, and it's just calling the model.generate from the and taking that output, again using tokenizer, decoding it, and then we are looking for the expected tool calls. We are collecting it, and then we are just checking if the base model, let's run before fine-tuning, if the base model is itself will be able to make it is capable model. So you will see on the base itself it's able to make the invocation. So till now, request more info. So this is what, like, if you don't want to fine tune it, that's also pretty much fine, because in most cases you won't require. Till now it's able to pick the correct tool calls on its own, which is really very interesting. And the only thing is it's not picking up the correct arguments and all. This is something which will get improved with the fine tuning. And if I'll see here, it's making a multiple tool calls. Request for more information, request approve product. So this is not the sequence we want. It could be request more information first, then approve product. So this is something it's important for us to fine tune now, because the order model does not understand. So it will be able to get it once we run the training. So for that, since this tutorial is very very big, I'm actually going to run this for only 10 steps. So you just need to see the SFT config, and this is the maximum length of generation, and we are choosing a batch size of 8, and gradient checkpoint is just a trick to save memory. Learning rate is very conservative, and we need to use BF16 for this T4 machine. If you have Ampere machine, then you can use FP16 as well, not a problem. So let's call our trainer, which is going to tokenize the whole dataset. It's preparing our dataset to be fed into the model, and once this is done, we are going to call the train and save the model. And let's also see after fine-tuning what are we seeing any improvement or not, although that model is already pretty much capable of identifying the correct tool invocation. So the problem of multiple tool invocation can be resolved with logically, like you usually in the OpenAI as well only takes the first tool call as the for their because there is also an uncertainty, so you can also avoid that. If that is a concern, you can always pick the first tool call, as there are tags available. If you see start of, you just pass that end of function call, that's it. That will solve the bigger problem of multiple invocation. So now it's going in the evaluation. is done, and our validation loss is good, and its accuracy is about 0.85, which is really good considering we have only given only 10 data point 10 patches actually, so 80 data points only, so that's kind of cool. And so what is expected from you? You should change and comment this and run it for at least 2 or 3 epochs on your dataset for really good quality. And you can also play around with learning rate. This is something which is going to increase your model performance up to even 90% as well. And as you will run this, it's going to actually save the model checkpoints and all. Everything will be saved in the folder as _final. Let's run it after fine tuning, and you will see it will start to make the invocation. So this is something that you can explore more with this notebook. Make sure to increase the epochs and all. So I'm just doing a demonstration. This code will perfectly work for embedding, and you just need to learn how can you strategize your data collection, labeling and all, and rest of the things will be transferable from this video. Thank you so much for watching this. I hope you had learned something from here.